This section of the notes is going to deal with spring mass systems, sometimes known as spring mass oscillators. So basically a mass attached to a spring that moves back and forth in a periodic pattern. We will discuss when this motion is horizontal and when this motion is vertical. Now, since we're dealing with springs, it's important that we recall Hooke's law. Remember from our Barbie bungee jump lab, we learned about that relationship that force has to displacement when you're dealing with something that's elastic like a spring or a rubber band. So when we stretch or compress a spring, we're applying the spring force. And the spring constant tells us that ratio, the amount of force we need to stretch a spring a certain distance. And then x in this case would be the displacement of the spring. So again, that relationship between displacement and force is a direct one, and it's held constant by that spring constant. Now, we use that term restoring force because when you stretch a spring, if I pull the spring like you see in the picture to the right, then the spring force would be to the left because that pull from the spring would try to move that block back to the left, which in this case would be a negative force because it would be moving leftward. That is why on this free body diagram you see here, we have three forces acting on that block. We have gravity pulling down from the center of mass. We have the normal force applied by the table upwards or the surface upwards. And then our spring force is to the left, so that would be kx. If we had compressed the block to the left, then the spring force would be to the right in the opposite direction. So whichever way you move a spring mass system, whichever way the applied force or the force of gravity, if it's vertical, is stretching or compressing the spring force will always be in the opposite direction and will always try to return the spring to equilibrium, to its initial position before the spring was either stretched or compressed. So again, that's where the restoring force comes into play, and that's what makes it simple harmonic motion. This time you should check out the mass spring oscillator demo that is posted in Classroom so that you can see these moving back and forth in that periodic pattern from being stretched to an equilibrium to compressed to equilibrium, and then repeating that over and over again. And the demo will then make those connections to Hooke's law as well so that you can see it. So definitely check that out. It is posted in Classroom below the note videos that I've created. There are some demos posted there that you will need to watch. So looking back at our free body diagram, let's just break down Newton's second law and its impact on spring mass systems. So linking together our laws, remember Newton's second law is F equals ma, our net force is equal to the mass times the acceleration. And since we have two directions here, we have vertical forces and horizontal forces, we need to break up our equations because we can only use our equations in one direction of motion at a time. So let's go ahead and write our F equals ma equations for this diagram you see here. Starting with the y direction, we've got our normal force plus, because of the sigma here, that means sum, it means to add. The negative force due to gravity, because that vector is directed downwards, and those are equal to each other, they're equal to 0, because the motion of the mass is horizontal, so there is no vertical motion, so the sum of those forces must be 0, because there's no acceleration. So my normal force equals my force due to gravity, or weight, and then if I want to just write that all the way out, my normal force could be calculated by doing the mass of the block times the acceleration due to gravity of that block on that planet. On Earth, that would be 9.8 or 10 meters per second squared. Moving over to the x portion, this is where we get our acceleration for our oscillating system, our system moving back and forth. So I have my spring force equals ma. I'm going to rewrite it using Hooke's law. And then I'm going to actually rearrange this one to solve for acceleration real quick so that you can see how acceleration is related to these variables. So if you look at this, k is a constant. So the spring constant is not going to change. A spring has a certain amount of stretchiness to it, and that is going to be the same no matter what. Now, as you can see here, there's an inverse relationship between mass and acceleration, like we would expect in a Newton's second law situation. So the more mass you have, the less it's going to accelerate, which makes sense because if something is bigger, you need to apply more force to get it moving because it has more inertia. If I look here at displacement, though, that's where things get interesting. The more you displace the spring, the larger the spring force gets, the higher this acceleration value is going to be. Now, if something is moving back and forth, left and right, back to equilibrium, compressing, equilibrium, expanding, that means that x, the displacement, is constantly changing for oscillators. That means our acceleration is going to be constantly changing as well. That means that we're going to have our largest accelerations when we have our largest displacements, when we're at our maximums or our minimums on a graph of that motion, that displacement. So that's just something to consider moving forward. Remember, when I say acceleration, I mean the largest change in velocity, because when you get to that maximum or that minimum, you're going to have to stop for a split second and turn around. So that's going to be a large change in velocity, therefore a large acceleration. This also means that when something is at its equilibrium position, when the spring is not stretched or compressed, when it's just at zero displacement, that there would be no acceleration. So that's just something to consider as we construct graphs moving forward. Since sine and cosine functions follow a set pattern, they're periodic, they actually describe simple harmonic motion to a T. So as something is moving back and forth, as a spring stretches and compresses, the motion can be plotted and it will resemble a sine or cosine function. You can really use either to describe simple harmonic motion, because all that's different is where it starts. A sine function starts at equilibrium, whereas a cosine function starts at a maximum. So you can use either. The formula sheet on the AP exam will use cosine. Now, just breaking down this equation, x would be the location in space of the system at any point in time of that mass. A would be your amplitude, the distance away from equilibrium. In this case, it would be the maximum value for that amplitude. And then we have a cosine function here, and 2 pi f for frequency, and t. Now, as you see here on the left, you'll see an omega. That's how it's going to look in college. We will link omega and 2 pi f in a second. But this is what we're going to use to plot where something would be over time, this function. And we're not going to go through why it's sine or cosine because it's due to differential calculus. So you're going to have to trust me a little bit on where the sine and the cosine come from, but it has to do with the fact that there are patterns when you take something called a derivative, when you break down a trig function, and sine and cosine functions follow that pattern where it repeats over and over again. So that is why we're going to use cosine or sine to describe position, velocity, and acceleration functions with wave or simple harmonic motion. Angular velocity is the rate at which something is rotating. So it's our angular displacement divided by time. So for simple harmonic motion, we can actually calculate angular velocity the same way we did for rotation. So if we're making one cycle for a trig function is 2 pi. So we have our displacement, our angular displacement would be 2 pi. We're going to divide that by capital T, the period, and that's what will give us our angular velocity. We've got an angular displacement 2 pi over a time, capital T. But our relationship between the period and the frequency is an inverse one. So you can actually also calculate angular velocity as 2 pi multiplied by the frequency if we combine those two equations together. So that is where the 2 pi and the f for frequency came from on that last slide. And the reason why we can do this, why we can use that periodic equation or 2 pi for this, is because of the way that sine and cosine repeat every 2 pi.